So let's start with the first experiment of this project. The idea is to hit the ball with an impulse, and that should theoretically excite all the natural frequencies of the ball, and then you record the sound and apply an FFT on it. And since an impulse is a constant function in the frequency domain, this type of excitation should give us all the natural frequencies of the ball. Here I have hit the ball and recorded the sound in my phone. After that, we will take the recording, load it in a file in Python, read it using Librosa, and apply an FFT on it. But I set SR to none so that Librosa doesn't change the sampling rate of my file. Since the default sampling rate of Librosa is 22 kHz, setting SR to none will not change the sampling rate of your file. After applying the FFT, we go and plot the time domain signal and the frequency domain. And here we got the natural frequencies of our ball experimentally. And if you zoom at each peak, you will see that each peak consists of two very close natural frequencies, as we saw in COMSOL. And the fact that you will have always two modes very close to each other, this is what causes the beating sound you hear when you hit a Tibetan singing bowl. In French, it's called the phénomène de battement. After extracting the natural frequencies of the ball that we got from this experiment, which is what we got here, now it's time to compare the experimental results with the simulation results. And to do that, I have prepared this table right here to compare the results. So you will see in the first column, you have the results coming from COMSOL, and in the second column, you will see the experimental results. So here for the first pair, we have an error of about 18%. For the third pair, you have an error of 4 or 5%. And for the fifth pair, you have an error of 4%. But we have a pair and a single mode that we did not observe experimentally in this frequency domain graph. And the reason for this goes back to the boundary conditions. You see, in COMSOL, we have set the base of the ball to be completely fixed. But in the experiment, the ball was simply seated on a plane. And this fixed boundary condition for the ball at its base made it possible for it to oscillate laterally, which we could see on the left, and vertically, which we could see on the right. So here is a clear example on the effect of boundary condition on the result of simulation.